We are continuing the properties of D block elements. Already we discussed 11 of them. Today, the 12th one, that is about electrode potentials. Here, M2 plus bar M standard electrode potentials. You know, when two electrons are added to a metal ion of positive charge 2, it will be reduced to the metal. Zn2 plus 2 electron gives Zn. Cu2 plus 2 electron gives Cu. Know it. And there are chances for the reduction of plus 3 oxidation state to plus 2. That is another possibility. Here we are considering only M2 plus bar M, standard electrode potential. You can see a graph here. Here, the negative value decreasing and it is becoming 0 after that positive value. That means as we move along the y-axis, the electrode potential, standard electrode potential increases. And you see in the case of first transition series, titanium, vanadium, chromium, manganese, first transition series. From titanium to chromium, there is a gradual increase in the electrode potential value. But in the case of manganese, it is reduced. Again, to ion, it is increased. And in the case of observed values, then comes cobalt, then a slight decrease in nickel. Again, in the case of copper, a positive value, 0.34, plus 0.34. In the case of zinc, the value is again decreasing. That means large negative value. This is a general trend. And the electrode potential depending on many factors. One is its ionization enthalpy, other one hydration enthalpy, ionization or atomization. Anyone, we can consider anyone, ionization or atomization. Then hydration enthalpy is another one. Then the stability of different ions, that also will contribute to the electrode potential. So among the first transition elements, you can identify only copper is showing a positive electrode potential. Copper cannot liberate hydrogen from dilute acids, you know it. And what is the reason for the positive electrode potential of copper? Because for the conversion of Cu2 plus to Cu, addition of electrons required, isn't it? Copper has a large tendency to undergo reduction. Why it is showing a large tendency to undergo reduction? Because for the removal of electron from copper, large amount of energy is needed. And that energy is generated by the hydration enthalpy. When copper forms bond with the water molecule, that process, Cu2 plus ion forms bonds with the water molecule, that process is known as hydration. Many water molecules will surround a positive ion. Energy will be liberated, that is known as hydration enthalpy. So when we compare the energy required for the formation of Cu2 plus and the hydration enthalpy is less. It is not compensating the energy required for the formation of Cu2 plus. So always the tendency is the reverse tendency. That means Cu2 plus will try to become Cu. Then only it will reach in a stable state. That is the reason for showing this positive electrode potential of copper. I think it is clear to you. And here, as I explained in the graph, the value is changing to less negative, or we can say electrode potential increasing. Is increasing from left to right in a period. Some variations you can see. And we have to explain why there is a variation in the case of manganese. We can explain it on the basis of the stability of D5 configuration. Mn2 plus, that is stable because of D5 configuration. If you want to convert Mn2 plus to Mn, addition of 2 electrons required. 2 more electrons required. Therefore, manganese is not showing a tendency to change from Mn2 plus to Mn because of the high stability of Mn2 plus. That is why there's large negative value as electrode potential. Then we can observe it in the case of nickel. It is slightly increasing. In the case of nickel, D8 configuration. You know, in the case of d orbitals, there is a splitting, 3 plus 2. After getting 3 T2G orbitals and 2 EG orbitals, one unpaired electron, when it is getting one unpaired electron, D5 configuration. Again, in the T2G, 3 more orbitals. Suppose all the orbitals are paired, then total number of electrons will be 8, D8. That also a stable configuration, and due to that stable configuration, it is showing a decrease in its electrode potential or showing a comparatively larger negative value. In the case of zinc, all of you know D10 configuration highly stable. So it has no tendency to change it to ZS. So these are some of the variations that we can see here. It is explained here, Mn2 plus and completely filled D10 configuration and 2 plus. And the case of Ni2 plus is related to highest negative enthalpy of hydration. In the case of nickel, it has high negative value of enthalpy of hydration, means large amount of heat energy will be liberated. That is a reason for the comparatively less electrode potential of zinc. We mentioned there are some other cases in which plus 3 ions will be reduced to plus 2. And this electrode potential, these portions are not very important because it is depending on many other factors. But these questions from the textbook, that is solved questions or indexed questions, you can expect for the examination. So you should be familiar with these questions. For example, you see one question. Why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? A very important question. Cr2 plus D4 configuration, Mn3 plus D4 configuration. But Cr2 plus, that is reducing, Mn3 plus is oxidizing. What is the reason? You know, Cr2 plus chromium, D4, 4s2. So when it is changing to Cr2 plus D4 configuration. And when it is removing one electron, it will get D3 configuration. D3 configuration means, in the case of splitting of d orbitals, 3 d orbitals will go to lower energy state, 2 to the higher energy state. So if it is D3 configuration, all the d orbitals in the lower energy state will get one unpaired electron or half-filled, exactly half-filled state. Therefore, in the case of chromium, D3 is a stable state. So it will give one electron and try to attain the D3 configuration. But in the case of manganese, if it will get 1 molar electron, it will get a D5 configuration. Actually, in the case of manganese, it is showing D5 configuration. So in the case of manganese, D4 is highly unstable state. In the +2, even in +2 oxidation state, manganese is in D5 configuration. But when it is changing to +3, it is going to unstable D4 configuration. So it has always a tendency to accept 1 more electron and to change it to D5 configuration. That is explained here in the textbook. You have to read and study this one. Don't forget to write it into your notebook. There is another index which you see. The E0 of M2 plus bar M value for copper is positive, 0.34 volt. What is possible the reason for this? We already explained. What do you have to say? High enthalpy of atomization, low enthalpy of hydration. That is the reason. Hints are given and you a little explain it. Trends in the M3 plus bar M2 plus standard electrode potentials. You know, in some cases M3 plus state is more stable. But in the case of manganese, already we mentioned M3 plus is unstable than M2 plus. In the case of iron, D6 4s2 configuration, D6, 3D6 4s2 configuration. When iron removes 3 electrons, it will get stable D5 configuration. That is more stable. So Fe3 plus is more stable than Fe2 plus. So in the case of manganese, where Mn2 plus is more stable than Mn3 plus, it has a large tendency to undergo reduction and to form Mn2 plus. So its value will be high. Standard electrode potential will be high. But in the case of iron, Fe3 plus is more stable than Fe2 plus. So Fe3 plus is not ready to change it to Fe2 plus. Means its reduction tendency is low. So its reduction potential will be low. Means the value will be large negative. The low value of scandium reflects the stability of scandium 3 plus. Just a noble gas configuration. 3D1 4s2 configuration, if all the electrons from S and D are removed, it will get a noble gas configuration. So that is highly stable. So Sc3 plus has not tendency to change it to Sc2 plus. But in the case of zinc, the value is high. If you try to remove 1 more electron from zinc, it will lose the D10 configuration. So Zn3 plus always has a large tendency to change it to Zn2 plus. So it is high value. And manganese also high value, already we mentioned. Mn2 plus is more stable than Mn3 plus. Iron, we mentioned. Fe3 plus is more stable, therefore the value will be low. The value for vanadium is related to the stability of V2 plus after T2G level. That is D3 configuration. So these are some points related to M3 plus bar M2 standard electrode potential. You have to go through these points only and find out the reason. Now, you read this question, E0 value and E0 value of M2 plus bar M ions are given. On the top elements, vanadium minus 1.18, M2 plus bar M values. chromium minus 0.91, manganese minus 1.18, iron minus 0.44, cobalt minus 0.28, nickel minus 0.25, and copper plus 0.34. Explain the regularity in the above values. Which are the, we discussed it here. Regularity you can observe in the case of manganese. The value is largely negative. From vanadium to chromium, the value is increasing, negative value is decreasing. But from chromium to manganese, again the negative value is increasing, or we can say the electrode potential is decreasing. And in the case of copper, large positive value. So already we explained it, you read and understand it. Why is the E0 value 4, the Mn3 plus bar Mn2 plus couple much more positive than? We explained it, and in the previous page you can see the answer. Okay. Now, how the higher oxidation states are stabilized. Already we discussed oxidation states of transition metal compounds. In oxidation state of transition metal compounds, we told up to +7 oxidation state. In the case of first transition series, up to +7 oxidation state is possible. But how it is stabilized? It can be stabilized by certain elements. Examples, fluorine and oxygen. Fluorine and oxygen has a special property to stabilize higher oxidation states. The highest oxidation numbers are achieved in the case of tetrahalides, for example, TiX4, VF5, and CRF6. The +7 state for manganese is not represented in simple halides, but in MnO3F, an oxyfluoride. So from this, what we can understand, fluorine and oxygen can stabilize higher oxidation states. What is the reason for that? The reason is that it may be due to higher lattice energy, for example, COF3, or it may be due to higher bond enthalpy, example VF5 and CRF5. In the case of Cu2 plus halides, iodides are not forming. The reason Cu2 plus can oxidize I minus to I2. Some points related to the stability of oxidation state. Cu2 plus can form halides, but iodides are not formed. Why? Because Cu2 plus can oxidize I minus to I2. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine due to the ability of oxygen to form multiple bonds to metals. So when you compare oxygen and fluorine, which is having more ability to stabilize the higher oxidation state, it is oxygen. Why oxygen is better than fluorine? Because oxygen has the ability to form multiple bonds. Okay, I think it is enough for today. Try to understand it. And if you have any doubt, don't forget to ask it.